Hello everyone. This lecture is exclusively recorded for third year BSc student of BK Birla College, Kalyan. This is mathematics class paper 1. In this lecture, we will state and prove Leibnitz rule, which is also called as differentiation under integral sign. So DUIS, differentiation under integral sign. So I may abbreviate this DUIS, differentiation under integral sign. So let me write down the statement of the theorem. So let f is defined on close interval a comma b cross c comma d, so which is a rectangle basically. So let's call this as a rectangle E on rectangle close interval a comma b cross c comma d. F is continuous on E if there are following conditions: dou f upon dou x exists and is continuous on rectangle E. Second condition, g of x is defined as integral c to d f of x comma y dy for all x belongs to close interval a comma b. Then the function g is differentiable. G is differentiable. So g is defined on close interval a comma b. So g is differentiable on a comma b, and the derivative of g, that g dash x is equal to, so this integral c to d d by dx of f of x comma y dy. So I should say here, instead of d by dx, I'll show here I will say dou by dou x. Now here I wrote only g dash, means dg by dx, because g is a function of x only. Here f is a function of two variable, so that it is not an ordinary derivative, it is a partial derivative. So in other words, this is same as integral c to d dou f upon dou x dy. So what it says that when you take the derivative on this expression, this integration and derivative can be swapped. So hence it is called as the name itself says that differentiation under integral sign. So you can swap the derivative and integration provided this hypothesis 1 and 2 get satisfied and f is continuous on closed interval E, f is continuous on rectangle E. Then we can have derivative g dash as integral c to d dou f upon dou x dy. Okay, so let's prove this. So to prove this, one should have the knowledge of Lagrange's mean value theorem of one variable. So I'm assuming that everybody is aware about, everyone knows the Lagrange's mean value theorem. So if not, you must recall the Lagrange's mean value theorem. Right, so let's write down this. It's given that dou f upon dou x exists on E and it is continuous. So you can see that it is given dou f upon dou x is exists and it is continuous on rectangle E. Right. So what is E? E is basically A comma B cross C comma D. Now if I fix Y from closed interval C comma D, then my f is will be a function of only, so f will be function of only x, right? So for each fixed y belongs to C comma D, I can say f of x comma y is function of x alone, and it is said that f is continuous and dou f by dou x exists. Dou f by dou x exists means when y is a constant, so it will be a function of one variable, and dou f by dou x will be now df by dx, so it is a derivative of f. So this would imply f is differentiable. So this would imply then f is continuous. I should say dou f upon dou x. Yeah, I should say f is continuous is already given at very beginning itself. Let me check the state. Yeah, it's defined and f is continuous is already given. Then f is continuous and differentiable. So why I'm saying differentiable? Because dou f by dou x exists when you fixed y. So when you fix y, then you are talking about the closed interval a comma b, differentiable on closed interval a comma b for each fixed y belongs to closed interval c comma d. Right. So f is continuous, f is differentiable, so you can apply the Lagrange's mean value theorem. So how will I apply the Lagrange's mean value theorem? So that's as such. So let h is not equal to 0 such that I am taking an interval x plus h comma y. So y is fixed, which belongs to my closed interval E. So by Lagrange's mean value theorem, there exists theta belongs to open interval 0 comma 1 such that f of, so we are applying on x to x plus h, so it is f of x plus h comma y minus f of x comma y is equal to f dash. So here f dash is dou f upon dou x at x plus theta h comma y. So if you remember Lagrange's mean value theorem, we had this like this: f of b minus f of a is equal to, so I should say here I have missed out something. Here h is also there, so let me write down this h times dou f of 1. So this is uh, b minus a times f dash at c. We say there exists c. This is a, so if f is continuous on closed interval a comma b, f is differentiable, uh, continuous and differentiable on continuous on closed interval a comma b, differentiable on open interval a comma b. Then we say there exists c. There exists c belongs to closed interval a comma b such that there exists c belongs to. So I can take on a little larger space. I hope you all are knowing this. F is continuous on closed interval a comma b. F is differentiable on open interval a comma b. Then we say this is open. Then we say there exists c belongs to open interval a comma b such that f of b minus f of a is equal to, here f dash c, so b minus a I will take this side into f dash c, f dash c. Now here you can see that instead of, I have taken b minus a as h and my b as a is equal to x and b is equal to x plus h. So here f is a function of two variables. So this anyway, this y is a fix everywhere, you can see. I have applied on x plus h. Now here x and h is basically b minus a. So here it is b minus a. And this theta plus h, c can be always represent that. We can always that is one of the form of Lagrange's mean value theorem. So we write here in the one variable, we write instead of c, we write a plus theta h. So we have a is here x and theta is between 0 to 1 and h is h is an incremented value that we all. So this was just I am just trying to recall your first year BSc. If you find any difficulties how you get this, we will definitely discuss in the class. Okay, so let me number this as 1. Okay. Now also it is given that f of x comma y is continuous on E. E is closed interval a comma b cross c comma d. Now I will fix x. If I fix x from closed interval a comma b, then f will be a function of c comma f will be a function of y alone, right? So for each fixed x belongs to a comma b, f will be function of y alone, right? And if it is y alone, f will be definitely continuous on closed interval a comma b cross c comma d, so it will be continuous on closed interval c comma d also. This would imply f of x comma y is continuous on closed interval c comma d for each fixed x belongs to a comma b. So if it is continuous, it is a function of one variable only. So this would imply the integral is possible. So integration y is limit from c to d. So integration c to d f of x comma y dy. This is exist because it's a Riemann integrable. Every continuous function is a Riemann integrable. Exist and well defined. In fact, it is R integrable, right? So if this is exist and well defined, then in given this g of x is c to d f of x comma y dy. So this g of x is exists. This means this would imply g of x exists and well defined for all x belongs to closed interval a comma b. Now what is my target? My target is to show that g is differentiable on closed interval a comma b, and further I need to show that g dash x is equal to integral c to d dou f upon dou x dy. This is what I need to show. So you assume that f is always function of x, though I had not written, but here I will write now. Here it is dy. So how to show g is differentiable? It is clear, that is to show that, that is to prove that limit as h approaches to 0, g of x plus h minus g of x upon h, this exists, ये value exists here, and this exist value is basically this integral value. Where does x belongs? X is any point from the closed interval a comma b. So well, I should exclude open, I should say it is open interval, that doesn't matter. Because at 8 point I need to define differentiable. So okay, existence equals to integral c to d dou f upon dou x comma y dy, or that is basically you can say that limit as, that is to prove that limit as h goes to 0, g of x plus h minus g of x upon h is equal to integral c to d dou f upon dou x at x comma y dy. I need to show this is this limit is this. So what I will do, I will basically say is that if the h approaches to 0, modulus this minus this approaches to 0. Right. So that is to prove that for every epsilon greater than 0, there exists delta greater than 0 such that mod h less than 0, mod h less than delta implies modulus of g of x plus h minus g of x upon h minus integral c to d dou f upon dou x at x comma y dy. This is less than epsilon. This is what I wanted to show. Right. So what I will do, I will consider this modulus and I will show that it is less than epsilon, and I'll assume that mod h is less than delta. So let's well, that delta we have to choose. Okay, so consider the difference. Consider the difference g of x plus h minus g of x upon h minus integral c to d dou f upon dou x at x comma y dy. This difference I am calculating. So this is equal to, so let me write down on the next line, that will be better. This is same as modulus. What is g of x plus h? Let me calculate this. I know my g of x. It is given as g of x somewhere. It is given, I think, in given fact. It is given. Yeah, I have already. G of x is integral c to d f of x comma y dy. Okay. So what will be g of x plus h? C to d f of x plus h comma y dy. That will be g of x plus h. So integral c to d. Now here f of x plus h comma y dy minus g of x will be c to d f of x comma y dy upon h minus integral c to d dou f upon dou x comma y dy mod complete. Okay. This is equivalent to saying that this mod integration we can club it, because we have seen that this integration exists. So f of x plus h comma y minus f of x comma y, this I have clubbed dy. I have taken this as 1 by h outside, and minus integral c to d dou f upon dou x at x comma y dy. Okay. So further this is same as 1 upon h. So this integral c to d will remain as it is. So f of x plus h comma y minus f of x comma y. This difference we have already calculated in 1. I think I have written it. Yeah, f of x plus h comma y minus f of x comma y is equal to h times dou f upon dou x plus theta h comma y. So let me write down this. It is h times dou f upon dou x plus theta h comma y dy minus integral c to d dou f upon dou x at x comma y dy from 1. Okay. Now this h and this h will get cancelled, because this 1 by h is multiplied to only this first term only. So what I will left with integral c to d dou f upon dou x at x plus theta h comma y dy minus integral c to d dou f upon dou x at x comma y dy mod complete. So this is further, I can club this in a one integration itself. So c to d dou f upon dou x plus theta h comma y minus dou f upon dou x at x comma y bracket complete dy. Further, this dou f upon dou x is continuous, so it is R integrable. So this can be further, this integration can be taken outside, and this is less than equal to modulus dou f upon dou x at x plus theta h comma y minus dou f upon dou x at x comma y mod complete dy. Right. Let me call this as number 2. Now we know that even the function it's also, so it is given that dou f upon dou x is continuous on E is a comma b cross c comma d. a function which is defined on a closed, a continuous function defined on a closed and bounded domain is uniformly continuous. That is one of the uh, standard result we know. The domain is a closed rectangle, so it is closed and bounded, so it is uniformly continuous. So this would imply dou f upon dou x is uniformly continuous on E. So when we say it is continuous, so how will I define continuity? So this would imply for every epsilon greater than 0, there exists delta greater than 0 such that, so f is a function of x comma y now here, such that you take any 2 points. So let me say uh, such that the distance between x comma y minus, let me say, p comma q, so here it is norm, is less than delta, would imply uh, this f of x dou f upon dou x is a scalar field, so that distance will be in a modulus dou f upon dou x at x comma y minus dou f upon dou y, so it's not dou y, it's dou f upon dou x at p comma q, this will be less than epsilon. So let's call this as number 3, right? So am I able to apply 3 into? Yes, I can apply 3 into, provided this norm of x plus theta h comma y and x plus comma y should be less than delta. So let's find out. So uh, let's find out the distance between x plus theta h comma y minus x comma y. So what is the distance of this? This distance is square root of, that's a distance formula, x plus theta h minus x whole square plus y minus y whole square. So what is it? It is same as under root of theta square h square, so which is equal to, yeah, it's a positive square, theta times mod h, you can say. Theta is always positive. Theta is less than between 0 to 1, so you can say replace theta by 1 less than 1, so it mod s, because since theta is between 0 to 1, so you can replace theta. So this norm is less than, is basically less than mod h. So what I will say, so choose delta such that, so choose delta greater than 0 such that mod h is less than delta. So if I use this, then I can apply 3 in 2, and this will definitely less than epsilon. So what I'll do here, I will say epsilon. Okay, let's do that. So from 2 and 3, what I got is as follows. 2 says that, ये कहाँ से, यहाँ से. From 2 I can say that modulus of g of x plus h minus g of x upon h minus integral c to d dou f upon dou x at x comma y dy. This modulus is less than integral c to d. I'm applying this in, so this modulus I will replace by epsilon whenever mod h less than delta. Okay, so this is same as epsilon times d minus c. So I should have this d minus c in the denominator itself. So let me take this d minus c here itself. So here epsilon upon d minus c. So that will not be a problem. So here epsilon upon d minus c, epsilon upon d minus c. So this will be epsilon. So what I got is as follows. So therefore, modulus of g of x plus h minus g of x upon h minus integral c to d dou f upon dou x at x comma y dy. This is less than epsilon whenever this basically mod h less than delta. So this would imply g of x is differentiable and the integration differentiating value g dash x is basically this component, and g dash x is equal to integral c to d dou f upon dou x at x comma y dy. So this completes the Leibniz rule. There is a corollary based on this Leibniz rule. I will just state that corollary, which will be highly useful for the problem solving. So corollary, let f is continuous on E, which is equal to a comma b cross c comma d. Suppose number 1, phi comma psi are function from closed interval a comma b cross c comma d are differentiable function. So these are the functions from they are scalar valued function. It's so differentiable and so I should say, just wait, my phi and psi are defined on closed interval a comma b to r only. Right. Second, g of x is equal to integral phi of x psi of x dou f upon dou x dy for all x belongs to a comma b. Okay, so I must say one more condition here, that dou f upon dou xy exists and is continuous on rectangle. So here one more condition I say, dou f okay, dou f upon dou x exists and continuous on E, and this phi and psi have a function from a comma b to r, and g of x is defined in this way, then definitely g is differentiable and derivative of g is as follows. Then g of x is differentiable on closed interval a comma b, and g dash x is equal to integral phi of x to psi of x dou f upon dou x. I think this should not be, this must be f of x comma y dy. Then g dash x is equal to dou f upon dou x at x comma y dy plus f of x comma phi of x into phi dash x dou phi by dou x, that is fine, minus f of x comma phi of x. So this is psi and this is phi. So f of x comma phi of x into phi dash x. So this formula will be highly useful for the problem solving, and in fact we have already solved example with the help of this formula. Okay, so there was a few corrections I wrote here, f of x comma y. So you please make dou f by dou x initially, but it should be f of x comma y. And I forgot to write this. So this entire generalized, this is called as in fact the generalized Leibnitz rule. This can be, this proof is not in the syllabi, but well, this will be highly useful for the problem solving session. So, thank you for watching the lecture.